Hi, I'm Dr. Jacob Hudis. Welcome to my Special Relativity Masterclass. This is video 1. In this video, the first in my Special Relativity series, I'll introduce Einstein's theory in a way that's clear, intuitive, and visually engaging. We'll start with the origins of the theory, looking at the classical paradoxes that demand a new way of thinking. One challenge I had when I first learned relativity was that the background and motivation were often skipped. This lesson aims to fix that, rather than simply repeating what's in the textbooks, many of which closely follow or copy Einstein's own writings. I'll use my own approach, one that I believe makes the material click for newcomers. Einstein's a hero of mine, but he wasn't known as a great lecturer, and his explanations in print, while brilliant, can be dense for beginners. I think it's not only possible, but necessary to find clearer, more intuitive ways to explain the ideas he introduced. My goal is to use pictures, animations, and thought experiments to build understanding in a way that's memorable, accurate, and just a little different from the standard presentation. Before I show you the applets, I want to share something very important, a way of thinking that's essential for relativity. In physics, there is no preferred reference frame for describing motion. If two observers are moving at constant velocity relative to each other, each is free to consider themselves at rest and describe the other's motion relative to them. This idea isn't new. It comes from classical physics long before Einstein, but it's the foundation for modern relativity. The applets on the next slide will make this concept much easier to see and understand. Before we can understand special relativity, we absolutely have to understand what an inertial reference frame is. This terminology isn't just background, it's essential. Without it, relativity won't make sense. An inertial reference frame is one where Newton's first law holds. If nothing pushes or pulls on an object, it stays at rest or moves in a straight line at a constant speed. Examples of an inertial reference frame include a parked car or a car cruising steadily down a straight road. In special relativity, we make key assumptions. Every observation we talk about is made from an inertial frame of reference. A non-inertial reference frame is different. It's accelerating, speeding up, slowing down, or changing direction. In these frames, objects can seem to move even without a real force acting on them. So we have to introduce fictitious forces like the centrifugal force. For instance, in a braking or turning car, you might feel pushed forward or sideways, even though nothing is physically pushing you. That's the effect of being in a non-inertial reference frame. So here's the first of several applets I've made that I'm going to show you in this presentation. In this applet, there are 3 cars. Car A is at the center, it's red. Car B is at top, it's blue. And car C is on the bottom, and it's green. When I hit start, the cars are going to be in motion relative to each other, and they're all in equally acceptable inertial reference frames. I'll hit start and begin the applet. Now I'm going to stop time. We're looking at the picture in the reference frame of car A. In car A's reference frame, they're at rest. They can always say, I'm at rest, and everything is moving relative to me. As you can see, the velocity of car A relative to itself is 0. The velocity of car B relative to car A is 2 meters per second. And the velocity of car C relative to car A is -1 meter per second. And so this is the picture that the person in inertial reference frame of car A would see. Now I'm going to switch to the inertial reference frame of car B. So from car B's perspective, they can say that they're at rest and everything is moving relative to them. So what is car B going to see? Let's start the animation. I'm going to pause time. Car B says they're at rest and car A and car C are moving relative to them. In this case, the velocity of A relative to B is -2 meters per second. So B sees A moving backward at 2 meters per second. Remember, in the reference frame of A was at rest and they saw car B moving to the right at 2 meters per second. The velocity of car C relative to B is -3 meters per second. Recalling car A's reference frame, car B was moving to the right at 2 meters per second and C was moving to the left at -1 meter per second. They had a relative velocity of 3 meters per second. The relative velocity has to be the same in all reference frames. Finally, I'll switch to the reference frame of car C. So now car C is going to be at rest. So in car C's reference frame, what will be the velocity of A relative to C? And what will be the velocity of car B relative to C? You may want to pause the video and think about the answer before I run the applet. So I'll start the applet. I'm going to pause time. And now the velocity of car C relative to itself is 0. Car C is at rest. The velocity of car B relative to car C is 3 meters per second. And the velocity of car A relative to car C is 1 meter per second. Here are some key points I want you to understand before moving on with this lesson. There's no preferred reference frame for describing motion. If two observers are moving at a constant velocity relative to one another, each can consider themselves at rest and describe the motion of the other relative to themselves. This is a classical idea that predates Einstein, but it forms the foundation for understanding more modern theories of relativity. Newton's laws of mechanics hold in all inertial reference frames. Imagine you're on a train moving at 15 meters per second relative to the Earth. Or equivalently, the Earth is moving negative 15 meters per second relative to the train. While you're sitting on the train, you throw an apple so it accelerates at 5 meters per second squared for 1 second. Inside the train, you see the velocity change from 0 meters per second to 5 meters per second relative to you. An observer outside the train, they see the velocity change from 15 meters per second to 20 meters per second. The apple is moving with the train, and an observer outside the train sees the apple moving with an initial velocity of 15 meters per second. Both observers measure the same acceleration, 5 meters per second squared. Both also agree that net force equals mass times acceleration. Newton's 3 laws work identically in all inertial reference frames. No experiment can reveal which frame is truly at rest.
If someone throws an apple inside a moving train, both a passenger and an observer on the platform see the same change in the apple's speed, so Newton's laws hold in both frames.
AcePhysics.org.
Fantastic.
Math and physics tutoring with Dr. Hudis.
In electromagnetism, unlike in Newton's laws, some forces depend on velocity. Different observers would measure different velocities for the same moving charge. And since magnetic force depends on the velocity, they would predict different forces. This would suggest the laws of electromagnetism aren't the same in all frames, with one person in one inertial reference frame seeing different outcomes than another. I have an applet on the next slide that will make this much more clear. This is the exact kind of puzzle that inspired Einstein's thinking about special relativity. The Lorentz force is QV cross B. We can rewrite this as QVB when the magnetic field and velocity are perpendicular to each other. Q is the charge, V is the velocity, and B is the magnetic field. The force depends on velocity. If a charged particle is moving into a magnetic field, when it hits the magnetic field, it's going to feel a force. The force depends on the velocity of the charge. If the charge is moving quicker, the force will be larger. This important example, along with the next slide discussing the speed of light, will make Einstein's motivation for coming up with the special theory of relativity click. If a person is at rest with respect to a wire and its positive nuclei, as is normally the case in everyday life, they see electrons drifting through the wire. This motion of electrons produces a magnetic field that wraps around the wire, going into the screen on one side and out of the screen on the other. Now imagine a nearby test charge moving upward along the screen. In this frame, the person would see the charge bend towards the wire, given by the Lorentz force law, F equals QV cross B. To recap, there's a person at rest with respect to a wire. That means they're at rest with respect to the positive nuclei. Current is flowing in the wire. Charges are moving upward. That creates a magnetic field into the page here. There's also a magnetic field coming out of the page on the other side of the wire. I haven't drawn that here. Now imagine there's a negative charge here moving up the page. That charge is going to move through the magnetic field, and because it has velocity, it's going to be pulled towards the right. This is standard electricity and magnetism. This is the Lorentz force law that you learn in high school. The person standing right here will see the charge move upward and to the right. Now I'm going to change reference frames. What if a person moves alongside the test charge in an inertial reference frame at rest with respect to the charge? In the new frame, the person is at rest and the charge is at rest. The wire is moving past them, its gold color marker line sliding downward. Here, the person would see the electrons in the wire moving upward more slowly, while the positive charge in the wire would be moving downward at some speed. Since the test charge is at rest in this frame, and the magnetic force depends on velocity, they would expect no magnetic force at all. The charge would just sit there, wouldn't move. But here's the puzzle. If we actually run the experiment, the charge still bends towards the wire in both frames. How can that be? If you were moving right alongside the charge, this is actually what you'd see. Something in this picture isn't quite right. We'll get to that later, because for now we're just exploring the historical clues that led Einstein toward relativity. But if you already know what's wrong, drop your guess in the comments. Would the electric and magnetic fields look exactly the same in both reference frames? The answer takes us straight into relativity, but we'll get there after we lay out the postulates. This kind of mismatch between what we expect to see and what actually happens is exactly the sort of puzzle that made Einstein suspect something was wrong with the classical picture, and led him to rethink how electricity and magnetism and motion fit together. This slide is titled The Light Speed Conundrum. You can derive the speed of light by combining Ampere's law with Faraday's law, which produced the wave equation for light. I haven't gone through that derivation here because it's widely available, but the key result is that the speed of light depends on only two fundamental constants, the permittivity and permeability of free space. This is a formula for the speed of light, And as you can see, it's a function of two fundamental constants. What's striking is that no reference frame is mentioned in the derivation. So we have to ask, do these constants change between inertial reference frames? Or is the speed of light the same for all observers? That's the conundrum. If c depends on the constants and the constants are the same in all reference frames, then the speed of light must be the same for all inertial reference frames. If the speed of light varies between inertial reference frames, then the fundamental constants must change between inertial reference frames, or there is one special preferred reference frame. Both options are troubling. Experiments show that all inertial reference frames measure the same speed of light, and this invariance is one of the core foundations of Einstein's special relativity. In fact, it's one of the two postulates of relativity. All of special relativity is built on two fundamental postulates. In physics, a postulate is a starting assumption about how the world works, how the laws of nature behave in a given situation. From these postulates, we work out predictions and compare them with experiments. If the predictions consistently match reality, the theory may be called a law. These are the two postulates of relativity. First, the laws of physics are the same in all inertial reference frames. No preferred inertial reference frame exists. Second, the speed of light is the same in all inertial reference frames. On this slide, I'll explain the first postulate of relativity, which is written here. The laws of physics are the same in all inertial frames of reference. Here's an explanation. If two people are moving relative to each other, they will still agree on the laws of physics. For example, one observer will not see a charged particle pulled to the right, while a different observer in another inertial reference frame sees it behave completely differently near a current-carrying wire. A second example is if one person measures a force on a mass and it accelerates, another person in a different inertial frame must also find force equals mass times acceleration. The laws of physics can't change because you're in relative motion. On this slide, I'll explain the second postulate. The speed of light c is the same in all inertial frames. Let's look at an example of Newtonian velocity addition. I drive past a baseball field traveling north at 25 miles per hour. Player throws the ball south at a speed relative to the ground of 70 miles per hour. What is the speed of the ball in my inertial reference frame? The answer is 95 miles per hour. This is the picture as viewed from the inertial reference frame of the Earth. In my reference frame, I can consider myself at rest, and the ball is coming at me at 95 miles per hour. Either way, the relative velocity between me and the ball is 95 miles per hour. Now let's look at a second example involving the speed of light. Driving at 1,000 meters per second, I turn on my headlights. The speed of light is 3 times 10 to the 8th meters per second. What speed do I measure for the light from my car's inertial reference frame? What speed does an observer on the ground measure? The answer is c, the speed of light. It's not the speed of light plus 1,000 meters per second. That's not the way it works. The speed of light is the same in all inertial reference frames. Einstein began with the idea that the speed of light is constant for all observers, no matter how they move, and adjusted the rest of physics to fit this fact. From his two postulates of relativity, he computed several profound consequences. Events that are simultaneous in one frame may not be simultaneous in another. Time between events depends on the observer's motion. Moving objects are measured to be shorter along the direction of motion. Speeds combine differently than in everyday experience. They never exceed c. Energy and mass are two forms of the same thing. E equals mc squared.
Thanks for joining me on this journey through Einstein's revolutionary ideas. In the videos ahead, we'll explore each of these 5 consequences: relativity of simultaneity, time dilation, length contraction, velocity addition, and mass energy equivalence, one at a time. Subscribe and come discover the universe with me.
AcePhysics.org. Math and physics tutoring with Dr. Hudis.